Yeah. Upside down. Good evening, everyone. Good. So today's topic is RAM apportionment. Before we start dwelling into the details of RAM apportionment, we'll just see where are we in the whole process of reliability. Because I want to again and again bring you down to the why are we doing all these things? Because everything, if you look at it in isolation, it looks very confusing that we do something we don't know. They come and they teach something, and each man talks on one topic. So, and we don't know why we are doing this. So, I want to clear that in your mind. So, I'll draw a small block diagram. You will be able to appreciate this, where we are and why we are doing, and where are the other things what you have learned in this block diagram. Now, the first one is when you start a project, you specify the goal. Specify goal. Goal means what? We said that day, Hyderabad metro, the punctuality will be 98%. Or you want to make a machine, the reliability over a period of 2 years' time will be 90%. Some specification you will give. This is the starting point. This is one topic which I will do later. How to specify the RAM parameters for a metro project. How do we specify this? That itself in itself is a question. We'll see. But presume now the specification has been given to you. What will you do now? You know that in the metro system, there are complex other departments. It's not one system. There is civil, there is electrical, there is mechanical, there is power. Many systems are there. So this parameter of, say, let's say you're given 98% punctuality is a target. So now I have to allocate this target. The first job I have to do is allocate this target: reliability, punctuality, reliability, availability, any parameter which is given. Allocate reliability in components of the system. Components here may not part, maybe subsystems. There are big systems like, I said, power, civil engineering. So it can be a big system, but it is a component of the total project. Now, this is not an easy task. This is what we are going to do today. But this is not going to be an easy task. But there are simpler ways of doing it. We want to teach some simple methods. Then, once you allocate what you do, you start designing. There are various methods of designing it. Then once you design the general thing in each department or each subsystem to do an FMEA stroke FMEA CA. I will just elaborate each one in a little while. Then once you do this, then ask yourself a question. Is the goals which is set here in the first block, is it achieved? Ask the question. You say the goals are achieved. The answer is yes, I have achieved my goal, what I have set for each subsystem. Then now RAM is over, safety is left. Then I take up the safety analysis. Safety analysis. Then you ask yourself a question. When you do the safety, again is the goal of safety. Safety also has got a goal. Is it achieved? If the answer is yes, then I can choose, I'm ready for producing the product or the equipment. If the answer is no, the safety goals are not achieved, I get a no here. Even here I ask a question, if the goals achieved as per the specification, it may be a no here also. In either case, what I do, I go back and do an iteration. What first I do an FMEA. If this answer is no, I go and do a failure mode analysis and try to improve either the reliability or the safety aspect. In FMEA, I think Irfan must have taught some aspect of it. The purpose of FMEA is what? To find out, to improve the system reliability, one, or is there any failure which will cause an accident, unsafe condition. So by doing this, I get this answer. Suppose I get the answer for this loop, or I get answer for this loop. If I don't get the answer, still after doing my FMEA, I'm not able to do it, then I look for a further go up. I do a design improvement. What is the design improvement method I will do? I select a better material. The material which can withstand higher temperature, the material which can withstand higher ambient conditions, higher vibrations, etc. I'd improve the design. Even this is not satisfying things, then I look back to, have I apportioned the things properly? Maybe there is something wrong in the apportionment. I have given to somebody an apportionment of a very high value, say 0.9995 times, which is impossible to achieve either by a design method or by doing FMEA, FMEC. I am not able to do because I cannot improve beyond 0.95. The nature of the product is like that. Then what do? There is no point allotting that product 0.99. So maybe I will give this to 0.95 and something else I will improve to 0.98 so that the product becomes okay. So I go back. So it is the whole thing I want to show is it is an iteration cycle. Allocate, design, analysis, answer yourself, have you met the goal? Yes or no? Yes, go for safety. Safety goal met, yes or no? Yes, no problem. No means go back to the thing. So it is a cycle. Today we are going to see this. Now, to recollect what all we have done so far in this whole loop, let us take the implementation or design methods. What have we seen? You've seen what is reliability, what is maintainability, what is availability, how it is, how to calculate MTTF, how to test MTTF, how to, I said, you start from the basic components from component, assume all the components and the things are in series, then you make a module, then put all the modules in the equipment, assume all the modules in series, then calculate the overall reliability, assume all the subsystems are in series, go to the system. That means things like reliability, block diagram, selection of the material. These are the things we have seen here, and how to check whether my design is okay. Analysis. Also, we have done how to do the analysis for this. And here also we do the reliability growth. After implementing, I make a prototype, go and test it and see whether I can achieve the target reliability which I have allocated to myself. So this you have seen in this area. In this thing you have seen analysis, for example, is RBT. I do the material selection. I do the things in series, parallel, and things like that. Then I did all those design methods. FMEA, what is that? To develop a prototype already developed for this job. Then you do the reliability testing here also. But how do you do the reliability test? In FMEA, you see a component, whether the component is, what happens if I remove the component, what happens if the component is broken, what happens if the component is short circuit or it is open circuit, will it give me a failure? And if so, is that failure very simple failure or it is a complicated failure? If it is a complicated failure, I use a better component. If it is a simple failure, then see I calculate all the lambdas together in series and find out what is the probability of that failure. Okay, it's once in so much, it's okay, I can live with it. So this kind of decisions you do in this. Some people do the reliability growth test here in design methods. Some people do the reliability growth at FMEA. Because after I do the analysis, I want to know whether I have improved or not. Some people do it at this stage, some people do it at this stage. So we saw what is that reliability testing, reliability growth. So it is applicable either at this part or at this part. Either this or this. But it has to be done. So once I do that, and then my final thing is goals here. So I can check with my target goal, then I branch off. In safety, primarily what do I do here? Safety is, here the focus is not on all failures. All failures I have seen in FMEA are design methods. Here the focus will be, which is that failure, which will create a safety hazard, and what corrective action I should take. There may be one or two failures which will do safety hazards. There are one or two failures, simply shut down the system and nothing happens. One or two failures can be an unsafe condition it can create. So I look for only those failures in safety analysis. I'm not interested again calculating what is the percentage. I do all those things, viable plotting. No, I don't do all those things here. I simply say, do I get, if this failure occurs, can it create an unsafe condition? How do we do this? One, I've already seen in FMEA, there can be some failure, some component fails. It will manifest itself in a bigger failure on the top. And that failure is not acceptable to me. You already got some hint and you improved it also. But now before going to the safety goal, see in that case, there are certain, in FMEA, the problem with FMEA is, it is a very good tool, but all failure modes are not foreseeable from that. So we come to a safety analysis. Here we do, the basic thing is, attention is, which failure can cause a safety hazard, or a combination of events. In FMEA, when I do one component at a time. What happens if a type of failure occurs in that component? In the case of electrical circuit, it is open circuit or closed circuit, or a connection is disconnected. I see one component at a time. I don't see multiple components. What happens? Component A fails, component B fails, component C fails, or one of the two fails, or three fails. This we don't see it. So we don't come to know the complete picture here. So what here we do, the safety analysis, is how to do that. I've already seen component level. Now I do a different approach, which you must have learned already. Fault tree analysis. Here I assume there is a top event. A boiler is there, an explosion takes place. This is a top event. In a boiler, an explosion takes place. So this is a top event. So now I go down. If this explosion has to take place, first thing, the pressure has to increase. Then only explosion takes place. And why the pressure will increase? There's something else which has failed, so that it keeps on heating. What is that failure? Or if the safety valve is there, has it opened? Not opened. Why is it not opened? So like that, first I assume a bad event on the top, and it's top going down. Why is this event happening? What are the systems which are so? It is a top-down approach. The FTA is a top-down approach, and I do only for the safety analysis. And FTA is not concerned with big thing about reliability, and mainly concerned with safety. Is the system safe? Is all the events are safe? I find some event who is a safe event. Then I do only the other reliability analysis, how to reduce that event. But if it's an unsafe event, I start looking at things more seriously. Why it is happening, which is the culprit for this. So this is FTA. This also I think Irfan must have touched upon. So this completes the whole process of iteration into the thing. So if you look at the whole reliability or RAM study, what we have seen, everything comes into this. You may ask, where is availability in this? The same process you do either for reliability or for availability, or for that matter for even maintainability, because MTTR, MTBF, they are all related to each other. So once you do for one, the others you can always relate it. I'll briefly touch upon after this how the availability is allocated, in case you want to allocate the availability here. Either you can allocate reliability or I can allocate availability. Now you see the whole picture now. Do the apportionment I am going to teach today. This block. Design methods, we have been teaching quite a bit on this, including reliability block diagram analysis. FMEA, Mr. Irfan has taught you. This, of course, there is nothing to learn here. You have to check the answer whether it is matching or not. Safety analysis, FTA is the primary tool. It has been done. Then again, here it is answer or not. So the iteration process. Reliability growth and testing comes either in this or in this, depending on what stage you want to do it. So we have seen now how the whole process of starting from the goal and ready for production or ready for commencing the project. You remember the cycle, whatever we have to do to achieve the goal, declare a state of readiness for production or start the project has been done by doing all these steps. So now perhaps it can give you a better picture. Why am I doing an RBD? Why am I doing an FMEA? FMEA I am doing to improve the reliability. Why am I doing an FTA? I do this to find out those events which will lead to an unsafe condition. Why am I doing the design? Because that is the job. I have to find a product. I have to find a project with subsystems which may give me the punctuality of 98%, 99%. So I have to design. How do I do that? Why am I doing reliability growth? Because I want to see whether the reliability which I have set for myself, whether I have achieved or not. So why you do all these things is to complete the cycle what I have indicated here. So this completes the whole picture of, yes, I have been thinking about it because individually, and I will also give you an assignment. RAMs, what is the relation between availability, reliability, and this and that. So further to this, if you now put that also, you will get a total picture of on the RAMs, content of the RAMs, their cores, their modules. Why do we do all these things? Okay. Having said that, now today's my topic is this block, reliability apportionment. Yeah. So we'll see apportionment today. It's also called allocation. As I said, it's not a very simple task. So it involves, we'll try to, not very simple. It involves, at this stage itself, a functional analysis, functional and RBD analysis. The starting point. Why RBD here? Here RBD I do it because I must know I have got a target of 0.98 reliability. Then I must know the subsystems are like this, or the subsystems are like this, or the subsystems are like this. A combination of these things. The subsystem A, B, C, D. Then only I can find out how to allocate this 0.9 to each one of these two. This overall thing here is 0.98. I have to find out what should I give to A, what should I give to B, what should I give to C. But for that, I must know a very approximate RBD, the reliability block diagram, the diagram only, no values, just the diagram, the combination, how do they exist. In the metro case, we saw that everything is in series. If any one system fails, everything fails. That is the assumption on which we did some problem also. So I must know, here I don't do the RBD analysis as such, but I must know how the systems are connected so that I can allocate the overall. So this is a very important step for doing this. Having said that, so as I said, the task is, a goal is given and you must allocate to different subsystems of the system. And while you do that, you must also think the cost should be minimum. I should not allocate in such a way I spend exorbitant amount in achieving that. So I should say that, okay, I will do this, give me 10 years time. It doesn't work. The time should be also the least so that my product goes into the market or the project is completed. You can't be telling for 10 years I'm designing. So because the allocation is very difficult for me, so I need 10 years time. That is not this. So as an engineer, you've got a very difficult task. So it is a very balancing act how to allocate the component system so the system meets its reliability goal with minimum time and with minimum cost, and it should meet the specifications. The overall reliability should be 0.98. if that is the example given to you. So it is a quite an involved task. So, but what we will do, there are many methods of doing this, work. But I will do, to demonstrate the principle, some simple method I will do. So the simple method will be, I left this question for you people that day. What is the best way to do it? Simplest way to do it? Now take the example of the metro. We have civil, we have power, we have the train control system, we have the rolling stock. And overall reliability and punctuality is given as this much. This is how the real metro system works. So now I have to allocate. The example we did as a homework twice was, we said that we calculated what is the punctuality of this, 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 and then we put together and saw whether I got 0.98 or not. The reverse we did. How did we calculate the punctuality of each one? We got the overall time, MTBF, number of failures, and there are various grades of failures, less than 2 minutes, less than 5 minutes, less than 10 minutes. Then MTTR was given in the specification to you. So I checked, verified whether each block fulfills a reliability. When you multiply all the reliability or punctuality, I get the overall punctuality. This we did. What today we are seeing is, I don't know any of these things. Those parameters are not given to me. I have been given this. So I have to now branch this into this view. How do I do this? So I posed a question. What is the simplest method you can think of doing this? Any guesses? My throat is bad today.
So one option is copying from existing systems.
Okay. One option is, that is something which our boys have nicely learned. Copy from existing systems. They'll all become good consultants.
What is?
Then next option.
So you have the target, you have got 4 subsystems.
In series, what is the best method of doing it? The diagram is there in the board, is it not?
Yes, sir.
The diagram is there, right?
Yes, sir.
I've got 4 blocks in
You
series,
got the target.
and overall I've given. So I'm asking you, what is the simplest method of doing it?
Simplest method.
Very simple.
Equal apportionment.
Excellent.
Is that
So,
what you
equal up.
Yeah.
You everybody equal. Four
divide by
brothers and
4.
sisters. The father has left with a lot of money. What do you do? Equally apportion. You don't bother about, I think that brother has got 10 children. This girl has got a big problem of this thing. That younger brother has got this many problems. So he should get more, he should get less. You don't fight like that. You say, oh, simple. Let everybody equally share the father's property. Isn't it? That is the simplest logic. So equally you allocate. So when you do equal, what is the thing? The overall is given to you. System. So R civil, R power, R SLT, R rolling stock. Equal to the total. So this is 0.98. So what will be each one of them? Each one will be what? So 0.98. If this multiplied by this, multiplied by this multiplied by this is equal to this, and I am saying all of them are equal. So each one will get what?
Calculate.
Comment, at least you tell me what will be an equation form. You don't have to give me the number. What do I do with 0.98? If there are two only, what will you do?
0.98 to the power 1 by 4.
Make here it will be 0.99 to the power 1 by 5. 1, 2,
4.
3, 4, 5. So it will be something, obviously it will be something higher than 0.98. So whatever it comes. So this is a simpler method. This may be a starting point. I start with this. Then you take the, told you know, siblings are there in a house, and then each one I alert. Then somebody intervenes and says, look, it's not fair. That poor fellow is fortunate, everybody is sick, he's got a lot of hospital expenditures. Why not we give him a little more? So if I give a little more to somebody, it will be at the expense of little less to somebody else. Yeah. So that means I look at now, why do I give a little more? I give a little more to somebody. Now the system is more complex and a lot of problems. And so the system has got more number of components. If any of the system here has got more number of components, obviously the reliability of that will be poor. Because lambda of that subsystem equal to lambda 1, lambda 2, lambda 3 up to n number of components. So if I got n different at different systems, so the fellow has got more number of components, deserves an allocation which is less reliable. In this case, we are talking about reliability. So more number of components means more failures. So I tolerate with less reliability to one thing, say this, and more reliability. Oh, civil, everything is good. Just put it there, it just works. It never fails. Simple, and the only few things are there. So I give a very high reliability to this. So this I may give, let's say 0.999. So at this expense of whatever answer I get here, at the expense, I increase this here, I decrease for somebody else. It's easy to achieve. So this is the first starting point. Everybody starts like this, equal method. You remember, I had given one example or one problem in one of those metros. I said the percentage of civil, electrical, S&P, rolling stock. I gave a percentage, if you remember. This takes some 20%, rolling stocks takes 75%, S&P takes some 50%, this takes some other percentage. Then I gave the overall unreliability I gave. Then I give a question mark I gave you. What will be of these things? So the next approach is, can I give a disproportionate percentage like this? And if I give, how do I give that? That you already answered. Copy from existing projects. What have they allocated? They give rolling stock 75% in one of the metros. They give this like this. So I use this. Once I know this, then it is easy now. I know the proportion in which to be allocated the total. It's a simple arithmetic to do it. Now, after allocating the first method of some reliability, let's say the simple method which we took in example. Three, four systems in series. Let's say there are three systems. 1, 2, 3. The problem is specified as this has got 0.5. I'm allocating this. I have allocated 0.8 to this. I allocated 0.9 to this. Let's see. I came to some very approximate thing of each thing I gave. What will be the overall thing? Can you tell quickly?
Point 36, sir.
Point
36.
36. But my goal was given to me, let us say, is 0.85. Is the goal given to me. So I have put one system, this is the system reliability. System reliability here, this is the component, subsystem reliability there, this is the component reliability. So we said, oh sorry, I gave a wrong problem. You take this 0.5 as 0.7, let's see what gets. This one is at 0.7, 0.8, 0.9. So this fellow is here, this fellow is here, this fellow is here. So what is overall now?
0.5.
0.7, point?
0.5.
0.5, don't be very good. 0.5. So I get the system reliability. If I take this as this as this, and this as 0.7, I get a system reliability of 0.5. This is my goal here. So this I allocated approximately. Okay, I copied some system, maybe I read it wrongly. So I said, okay, 0.7 here, 0.8 here, 0.9 here. Then what do? Then first it has come to 0.5. Whereas my goal is 0.85 here, somewhere here is the goal. So I would reach that. So what do? I look at this. Okay, let me improve. This is already 0.9, this is 0.8. The lowest fellow is 0.7. Is there a way of improving this by better components, better systems? I do derating the system. I select military components, top specification. So there is some scope for improving this fellow. So I try to improve this man. So component 1, this is 1, this is 2, this is 3, let's say. The 1 is at 0.5, 0.7, sorry, 0.7 here. Is at 0.7 and is contributing to this. So if I improve 0.7 to 0.8, 0.9, 0.99, 0.95, what happens? Component 1 I keep on improving. Let's say the extreme case of I go to 1. I cannot go beyond this. So let us work out what happens. I did this to 1. This fellow is 1. This fellow is 0.9. This fellow is 0.8. So it is 0.72 still. Still I have not reached. Even if I improve this lowest fellow of 0.7 to 1, I improve the reliability of one block. This is component 1. I improve the reliability. Even if I go to an extreme value of 1, still I am not able to touch 0.1 multiplied by 0.9 multiplied by 0.8. Still, it's only giving me 0.72. It doesn't give me the reliability goal. So similarly, I take one by one. Okay, this I come to some point here. 0.19, 1.0 is not possible. So I leave this here, say 0.9 something. So I get an altered value for 0.9 plus something. And that is the best I can do with that guy. So I can't do anything more than that. So I leave it at that. Then I take the second fellow. Then I try to improve him. This already reached 0.9. I improve. I come to some value. Then also I find that I don't get 0.85. Then I took third fellow, though it's very difficult, he's already in 0.9. So I try to improve some value I get. So even after all these improved values, I may not get 0.85. Now I have taken now one at a time. to do this exercise. If there are 10 subsystems, somebody can say, why not 2 at a time? Why not 3 at a time? Why not 4 at a time? Improvement. This is a very long iteration process. We'll get fed up of doing this. So people thought of how to do some more better method of doing it. That means, what are the things? Things are the complexity of the system. Our system means here the blocks, complexity of these blocks, or the number of components these blocks have got. If I can somehow accommodate the complexity and the number of components into my equation of the overall system is product of individual system, I equal to 1 to n. The symbol is for product, you are aware, I suppose. The symbol means it is product of what is coming here. That is product of R1 into R2 into R3 into Ri. Okay. So, in this, all I have to do is there a method of giving some weighting factor to each, an importance to each, depending on the number of components and the complexity of the system. Complexity. The system has got more components and more complex, give a value of R which is less. The system has got very simple, a few components, you give a very high reliability to that. If it's got medium, you give a medium value. So they said, okay, these are the two underlying factors which will deserve to be paid attention. We're allotting the values of R1, R2, R3. So this is the principle on which it is developed. Then, of course, the more complex methods are there, because it is through software programs where I include the cost also. If I do this, what is that cost? Because they have got multiple solutions. This equation has got infinite number of solutions, not one solution. Infinite number of values to R1, R2, R3, Ri will give me Rs. Out of that infinite solutions, which can be the minimum cost, minimum time, is a very difficult task. So people thought we do some basic assumptions and do the allocation to the subsystems. So based on this principle, there are two systems which are predominantly used. One is what I think is called ARINC, there's some Aeronautical Research Institute or something. They came up with a system method. Then there is called an AGRI method. Called the AGRI method. These are the two basic methods which are used. The aeronautical something, I'm not remembering where it is. This is the AGRI method is there is an advisory group. Advisory group on the reliability of electronic equipment. There is a group which was formed to study this problem of how to do this allocation. And they came up with a method taking the complexity and the number of components into account. This Aeronautical Research Institute did their own some method. He said, yeah, there is a problem in our hand. How do we do it a little more scientifically? So these are the two popular methods used. Slightly, this is slightly better than this. In order of priority, you can say this and this. But this is a little more complicated, but gives me a better allocation. So I will just briefly touch upon these two methods. How do they do that? The RINC method, INC method, here they do, in some reliability, they do the failure rate. Now if I have got n systems, just recollect. Yeah. I've got n systems with failure rates lambda 1, lambda 2, lambda 3 in series. What will be the overall thing? The overall lambda will be what? Assuming constant failure rate, what will be the overall lambda? Lambda 1, lambda 2, lambda 3, they are in series. So what will be the overall lambda of the system? The overall failure rate is R1, R2, R3 multiplication. The overall failure rate will be?
Product of the,
Hmm?
it will be the product of all the lambda values.
Whose answer is this?
Akila,
Akila's answer.
yes.
Akila, go back to the same basics. R1 equal to e power minus lambda 1 t into R2 equal to e power minus lambda 2 into t into R3 is minus lambda 3, sorry, it's e power lambda 3, and R1 is what? E to the power of minus lambda overall into t. This is the equation. So what is the relation now between lambdas?
The sum,
E to the power minus t is common for everybody. So I
sum of
take
all
this out.
lambda. Sum of all
Lambda 1 plus
lambda.
lambda 2 plus lambda 3. So lambda equal to? So the lambda here is equal to what?
Sum of
T is common. T is common for both sides.
yeah, sum of all lambda values.
So lambda is, so here the lambda is sum of lambda 1s. Lambda 1, lambda 2, lambda 3. So if I do failure rate, the system failure rate is sum of the individual failure rate. If I take the reliability, system reliability is a product of reliability. Okay? I think these are all the basic relations we established in the beginning. Maybe we have forgotten. So it is the problem now reduces I equal to 1 to n. The symbol used for a system total reliability is normally in a portion is star, lambda star. That is a system. System reliability should be less than or equal to lambda star. What is this lambda 1 star? This is individual allocation. Individual allocation or apportionment. So if I add up all that, it should come to system is a system value. I am doing allocation now. I don't know whether it will meet or not. That's why I have given the star value. So lambda 1, lambda 2, lambda 3, lambda n. That means lambda 1 star. I am allocating this lambda 2 star plus lambda n star should be less than or equal to lambda star. In reliability terms, R1 star, R2 star, R3 star should be greater than or equal to R system star. In the case of failure rate, it will be less than or equal to. I have told you the equation also. How to get this. So this is the, so Arendt's method took this equation and see how do I solve this. How to allocate? Here again infinite solution. A plus B plus C equal to some constant. What is the value of A, B, C? Unless I give the relationship, you need three equations to solve that. If A, B, C are unknowns, or X plus Y plus Z is a constant. Unless I know the relation between X, Y and Z, I cannot find a single answer. Any number of answers I can give. Infinite solution. So same thing here also. So what then they said, okay, this we have to solve. How do I solve this? The method they adopted is assume a weight factor. Weight factor Wi, the weighing factor, to each subsystem. Then if I know this, how to calculate, how to know this value, then it is easy for me to allot. The ith subsystem I can allot star value, allotted value will be what is the weight factor of that system, subsystem, and the overall failure rate is given to me. Overall failure rate is given to me. Individual failure rate I am finding out here by through a weighting factor. This weighting factor depends on number of components. We have a problem. Are you getting it?
Yes, sir.
Number of components.
No, now it stopped.
Stopped. Huh?
Yes, sir.
Okay. Shall I invite again?
Yes, sir.
Okay. I have to also create now. Yeah, I've sent it.
Yes, sir. We can see the whiteboard.
Can you see the whiteboard?
Yes, sir.
Okay. Now the purpose is to calculate the weighting factor. Once I know the weight factor for each subsystem, then I can allot. How do I allot this? I don't know whether it was coming or not. I will rewrite. So for any system, the allotted value will be the system weight factor, into lambda, overall system failure. This is given to me. The overall system failure is given to me. This is given. Somehow I calculate a weight factor. I multiply by the weight factor. I get for the ith system. Ith system weight factor is Wi, and the ith system failure rate is lambda I. And lambda star is overall is given to me. Now the question remains now is reduced to one single factor. How do I do this? So as I said, this will take into account first the system problem we defined. There are two things. One is the complexity, other is the number of components. These two, if I can incorporate into this, then I get it. So this method said, let me not do too much complicated work at a time. Let me see the number of components only I will achieve. Number of components more, the failure rate will be more. Number of components less, failure rate will be less. So what I do, to find out this, first I know what is the system. I know what is the system. So in the metricals, I know electrical, I know track, I know SMT, I know rolling stock. So I take each block, electrical. I don't worry about what is the overall target. I go to the designer. So I am now the electrical designer. I have given him, this is your metro electrical system. You copy from other systems or you buy from the market, you go to the vendors, find out the failure rates of each of your transformer, each your switch gears, failure rates, all you find out. You find out what is your lambda electrical. You can find out because this contains subsystems. It contains subsystems. And each one subsystem contains a component system. So I find out the failure rate of all these things either by my experience or from manufacturer, or there are handbooks available. There are handbooks available. I see those books which will give reliability or failure rates for various components. There is mechanical ones are there, electronics ones are there. So if a switch you take, you can find out from the handbook what is the failure rate of the switch. Or the manufacturer will tell you what is the failure rate. So you get all those things. You work out. Don't worry about the apportionment. You work out what is that you can achieve. So similarly for each system, you tell individually you work out what is that you can achieve from the current state of art of the technology, the product available in the market. You find out what is the failure rate of each of these guys. So then they said it is simple. Once I do that, the weighting factor will be I equal to 1 to n systems are there, and lambda. Lambda I can calculate. I am not worried about now. For a moment, forget about your apportion method. You are just asked to design. I want a metro power supply system. What will you do? You go to the manufacturers, take their failure rates, and you calculate. So I can calculate for each subsystem like that. What is the value I can achieve in the market today? Then the individuals, once I know, then I put sum of all these things. So the individual divided by the sum will be the weighting factor. Is it not? The bills are not. I am not opposing anything. Each one is allowed to design yourself. You design. Each one of you come with a value. For electrical fellow comes with a value. Track fellow comes with a value for itself. SNT comes with a value. This fellow comes with a value. So everybody comes up with a value. It's possible to design without giving any goal also. Once I do individual components, the weighting factor is the ith component divided by sum of all. Because a fellow who has got more, the fellow who's got failure rate is more, the high failure rate, because he's got more number of components. So the WI will be big. That means the final equation, when I allot, now I allot. Once I know this, now I say forget about your calculations, mister. Now yours will be WI into lambda star, which is given to the system. This I got only from you to design originally. And from that I say, now forget about your design. I am allotting you a value, this, which is equal to this. Now you go and redesign now. You improve what you want. So you gave me an I, W, lambda I. Then each one of you gave me lambda I. So I put a weighting factor and give you this. That means what? if somebody gives me a failure rate which is high failure rate, he will get a greater WI and he get a failure rate share also more. That means he can produce a system which is little less R. More lambda means less R. Because obviously, if somebody comes with a high failure rate, that means he's got more number of components. Because lambda is lambda 1, 2, 3, 4, 5. He has got n number of components. N is very high. So he will get a very high individual failure rate. So he gets a better weighting factor, higher weighting factor. So the overall also he gets a better. This is simple RMC method. Now I'll give you an example. What's the time left?
It's already 1 hour.
1 hour over?
Yes, sir.
Okay. So I'll give you a simple method. Just a very simple assignment based on this. There are 3 subsystems. Lambda 1 equal to 0.003, lambda 2 equal to 0.001. Failure rate, these are all failure rates, that means failures per hours. Lambda 3 equal to 0.004. These are all failures per hour. This is individually calculated. Each engineer calculated his system and came up with my lambda is this, my lambda is this, my lambda is this, overall lambda for his subsystem. The mission time equal to 20 hours. And the reliability requirement 0.9. Now we have to find out lambda 1 star, lambda 2 star, lambda 3 star. These are the calculated values depending on the components available in the market. Now, but the management says this is the overall reliability I must get for a 20-hour thing. Now, each one will get what value of this is the problem. So, how will you tackle this problem? I have got R of 20, mission time 20 hours equal to e to the power of minus lambda star, the total system ke liye lambda star failure rate into 20. This is 0.9. This equal to is given. So I can find out what is from this, what is lambda star. Lambda star, you can find out from this equation. Once lambda star is given, then go to ARINC method, find the weighting factor. Weighting factor will be this divided by the total what you got. This the lambda star weight for this, the weighting factor W2 will be the total individual of that double lambda 2 divided by the sum of the lambda 2. So you will find now different values of lambda 1, lambda 2, lambda 3 here. Lambda star 1, lambda star 2, lambda star 2. You will find a different value from what you have calculated, what is given in the problem. Okay. So this means what you get the answer here is the reliability or the failure rate of this system you must achieve. Now you have been given the problem. First you are all to work out the failure rates. Based on that, I get a weighting factor. Based on the weighting factor, I will give you reworked failure rate star. Then I'll tell you, now you design your system to suit these values. If I do that, then I achieve this reliability of 0.9. So this is the ARINC method. So just kindly work out the simple problem. So tomorrow, before starting, we see what is the star values. And then we'll proceed on that. Then you can say what is the reliability of that system. Once the lambda 1 star is known, I get the reliability of the 1, I get the reliability of 2, reliability of 3, and then I multiply, I should get 0.9. You may say that already I've got lambda 1, lambda 2, lambda 3, why don't I get it? If you put it, you won't get 0.9. That's the issue. If you put lambda 1, 003, lambda 2, 003, 00, this, you add up all the 3 and put e power minus that value, you don't get 0.9. This I have given or I have worked out only to find out what will be the weight of all these fellows. So according to the weighting factor, as I said in the example, a family is there, 4 siblings are there. So each one has got different problems. So that is, so I have to decide a weighting factor to each one. So first I hear what is your problem, I work out this. I hear the second member, what is your problem, I work out this. What is your problem, I work out this. But the overall then doesn't come to me. The answer overall sum, if I divide in this ratio, I don't get the amount I have got in total. So what I do, okay, these are all your problems, I have heard you. Now I am going to work out a weighting factor for each one of you, and I will apportion as per the weighting factor. So this is the, once you know the weighting factor, from the weighting factor, you get the lambda star values. Lambda star values you get the reliability of the system e power minus lambda star, because mission hour will always be given. So I can work back what is the reliability of each of the components. There are 3 components here. I can work out, and that is my goal set. The first block of the today's block diagram. So I have set the goal, each one how much I should give by this method. So this is a simpler method of doing it. Tomorrow briefly we will see what is the agree method, AGREE method. How do they allocate? They are also doing something like this, maybe a little more. All of them are involved in calculating, finding out the complexity and component levels. How important some components, subsystem may not be important. Doesn't matter. It works. Say the missile one. If I want to fire a missile, there are some systems which needed only, their reliability is needed only for firing the missile, not for the entire path of the missile. So I can give a low reliability. It just fires and that's all. The system is over. Ignite, over. It doesn't follow the entire mission time. The mission time may be less. Once the mission time is less, then I can take chance. I can give high lambda to achieve the same reliability. Lambda into T e power minus. So I can give a bigger, higher failure rate because T is very small, only maybe few minutes. So I can give a high failure rate. So the agree method basically takes into account complexity and the importance. How important this guy is. If he has to work only for a short while, maybe I can give a more larger failure rate. So these two, they also take these two into account, and they came up with methods not so complicated. So it's fairly simple. So they came up with another method. So these are the 2 methods I'm going to adopt. There are many other methods. They are all research oriented. That is not our interest. Okay. So 3 methods of solving this apportionment is copy from other systems and check whether you are okay with it. Second is, if you are not satisfied, do ARINC method, do agree method, allocate the subsystem reliability goals. Now after doing all this, the question is, I allocate, then I multiply R1, R2, R3, Rn. I don't even then get it. I follow agree method, I follow this method, still it is not coming. Then what do I do? I'm stuck up with the problem. Then now seriously look into, maybe I will provide a redundancy. So this component electrical system, with only one transformer, I'm not able to solve it. Target is given to me, I'm not, so I will put 2 transformers. If one fails, other will work. Then I can achieve, but this is at the cost of money. So what is it? This cost of money. But there's no other to go. I agree method I followed, this method I followed, I allocated, I copied from other things. Still I'm not able to achieve the equation equality. So what do? I look at the system. Can I go for a redundancy? If I get a redundancy, maybe the reliability will improve. Definitely it improves, you know it. If I do the two things in parallel, reliability is better, but it is at a cost. But the same thing if I do in a locomotive, if I put redundancy, think of the weight. It will carry more weight. If I put two converters inside this to improve the reliability, definitely the weight of the loco will improve. Not only the cost, the weight also will increase. Weight means I have to carry more load all the time. That means more fuel. The running cost is going to be high. So these are the issues people think of for research areas. How do I do it? But for our purpose, we allocate. Not satisfied, we go for redundancy. There is various methods of redundancy. I do not know whether they have taught you or not. Just we will touch upon the methods of redundancy later when I come there. What is the method? Hot standby, cold standby, active, inactive, 1 out of 3, all those methods are there. We'll see things. At least you must know redundancy. There are methods available like this.
So Mr. Khan has covered redundancy.
Yeah, he's covered. Okay, that's good. So if after all this allocation, if I don't meet my target, if I don't, the equation is not fulfilled, then I have nothing to do but to go for looking at my design. What can I do now? Can I go for redundancy? Because I already checked what is the best design. Component I have substituted, higher value I put, simple method I followed, less number of components I have done, but still it is not coming. So I do a redundancy introduction. So definitely the equation will be solved. So this is all about apportionment. So tomorrow we'll see one more simple method of agree method, how to solve this equation, which has got n number of solutions. Okay. So this assignment is very simple. You do it, and then tomorrow we'll start from the answers of the assignment. We go to the agree method. Once I complete agree method, I will simply give some introduction to how to. Now I have talked only about reliability. Reliability or lambda, one of these two. I talked about these two. Similarly, A, availability. How do I apportion availability? There are some simple methods because availability has got a factor MTTR. Lambda known, MTBF is okay, I have done all those things. But availability allocation, you would also bring in MTTR. So how do I factor that MTTR thing into account? We'll see a simple example and a simple method I will tell you how to do that. So if the goal is reliability, you do this method. The goal is availability, the same, it's a similar thing. There are no difference, only the symbols are different. But a little factor of MTTR has to be taken into account because MTTR defines also the availability, not only MTBF. Okay, I sign off now. Tomorrow, same time, we will see. Okay?
Okay, sir. Bye, sir.
I sent you a mail, Binay.
Okay, I'll check it, sir.
Yesterday I sent. Remember?
Yes.
That Harinika,
Yeah.
the paper is accepted.
Symposium, yeah. So we'll have to download that format and make the presentation.
Yeah, I have to download the format, find out.
Yeah. They said after first it will be available.
Achha, you already did that.
Yeah. So after first it will be available. So then we'll download and make.
Is that the only doubt I've got is that Harini, you please find out from her if you have the number.
Yeah.
I went through the various links they had given.
Yeah.
I